You may be surprised to learn that treatment of wastewater is a relatively modern practice. Although sewers to remove foul-smelling water were common in ancient Rome, it was not until 19th century that large cities began to understand the necessity of reducing the amount of pollutants in the used water they were discharging to the environment. Despite large supplies of fresh water and the natural ability of surface waters to cleanse themselves over time, populations had become so concentrated by 1850 that outbreaks of life-threatening diseases became a commonplace. These outbreaks were traced to pathogenic bacteria in the polluted water. What happens in a wastewater treatment plant is essentially the same as what occurs naturally in an ocean, lake, river, or stream. The function of a wastewater treatment plant is to speed up this natural cleansing process. The practice of wastewater collection and treatment has been developed and perfected, using some of the most technically sound biological, physical, chemical, and mechanical techniques available. As a result, public health and water quality are protected better today than ever before.
Process flow diagram. There are 4 stages to treat the wastewater: pre-treatment, primary treatment, secondary treatment, and tertiary treatment. The raw wastewater is sent through a bar screen to remove large solid objects. Then it will enter the great tank to allow small materials that cannot be caught by the bar screen to settle to the bottom. All the collected debris from the pre-treatment process is disposed at a sanitary landfills. The screen wastewater will go through primary treatment, where this process involves physical separation of solid and greases from the wastewater. In the primary settling tank, the wastewater will be held for hours to allow solid matter to settle at the surface of the tank, which is also called sludge. The sludge is removed by large scrapers and is pushed to the sludge holding tank and later pumped out for further treatment. The remaining water is then pumped for secondary treatment. Secondary treatment involves biological treatment process that removes dissolved organic material from wastewater. In aeration tank, air is pumped to mix the wastewater with sea sludge, which fuels the growth of bacteria that uses oxygen and the growth of microorganisms that consume the remaining organic materials. Liquid mixture is sent to clarifier. In clarifier, solids settle out to the bottom, where some of the material is sent to the solids handling process and some is recycled back to the aeration tank to treat incoming wastewater. Treated water is disinfected by chlorination and then it is sent out for wastewater reuse activities or to discharge to environment.
This is a closed-loop aeration tank. An appropriate food to microorganism ratio is necessary to obtain proper performance from the activated sludge process. So, the control variable in aeration tank is food to microorganism ratio. During aeration phase, specific bacteria eat the specific food. For the process to work properly, the manipulated variable that the operator must control are the number of organisms and the dissolved oxygen in the aeration tank, and also the treatment time in the aeration tank. A shortage of dissolved oxygen will kill the microorganisms, so the DO concentration in the aeration tank must be properly controlled. A DO analyzer is used to continuously measure the DO concentration. The disturbances that affect the performance of the process are pinpoint flux formation, filamentous bulking, dispersed growth, and zoological or viscous bulking. To ensure a good balance between food and microorganisms, the bacteria settled in the clarifiers are continuously returned at the inlet of the tank. Clarifiers or sedimentation basins are settling tanks built with mechanical means for continuous removal of solids being deposited by sedimentation. The control variable is the water turbulence in the tank. The manipulated variable is the water inlet and outlet velocity. Baffles are used to prevent fluid velocities at the tank entrance from extending into the tank. The solid particles are kept in suspension in water as long as it flows with sufficient velocities and turbulence. Sedimentation removes blocks by slowing the flow of water and decreasing turbulence. The heavier flock particles drop to the bottom and clarified water is collected from the top for filtration. There are 4 parts in this tank. 1. Influence zone decreases the velocity of the incoming water and distributes the flow evenly. 2. The settling zone provides calm area for suspended material to settle. 3. The effluent zone provides smooth transition from settling zone to the effluent flow area. 4. Slush zone, where settled solids are separated from the other particles in settling zone. Slush holding tanks provide storage and blending for the thickened with activated slush, primary slush, imported slush, and scum before further processing. Most holding tanks are equipped with alarms that will sound when they are nearly full and will require pumping shortly thereafter. Level of slush is the control variable. The inlet and outlet of the slush from tank are the manipulated variable. An ultrasonic level transmitter is installed to perform continuous level measurement for uninterrupted monitoring of slush volume. The disturbance is when the waste flow rate changes due to pump failure or blockage.
This is a proposed control for aeration tank. Aeration is an activated slush process based on pumping air or oxygen into a tank. This serves to promote the microbial growth in the wastewater. The microbe feeds on the organic material, forming flux which can be easily settled out and be removed from the aeration tank. As you can see in this case, the inlet wastewater stream is the disturbance in the control system, whereas the inlet oxygen stream is the manipulated stream. As you can see, a typical feedback controller is being introduced into the oxygen stream with flow control and flow transmitter. But to increase the performance, a ratio station is introduced into the system. The equation of the ratio station is shown as this. RD is the desired ratio. SU and SD are the spans of the flow transmitter for the manipulated and disturbance streams respectively. The reason why radio station is introduced is that with the presence of an ideal ratio, we can control how much oxygen is needed to flow into the system. By having an ideal amount of oxygen flowing into the tank according to a specific ratio, we can prevent the microorganism from reproducing too fast as the oxygen is always in excess. This also increases the economical feasibility as oxygen is very expensive. The valve for the oxygen stream should be filled close, as if the valve is faulty, the expensive oxygen will not go to waste by flowing everything into the aeration tank. For the outlet slush stream, a pH control is introduced, so if the pH in the tank is deviated away from the set point pH, the valve will open up and let the sludge to flow through into the sludge holding tank. The position of the pipe should be attached at the bottom of the tank because sludge has higher density compared to water. Hence, they will always be at the bottom of the tank. This will ease up the process of removing the sludge. The valve should be filled close because when the valve malfunctions, both the sludge and treated water in the tank will not flow into the sludge holding tank, as if there is no sludge in the tank, water will be flowing out through the pipe. As for the outlet treated water stream, a level control is introduced. Hence, if the level inside the aeration tank is higher than the threshold, the water will be able to flow out of the tank without the tank being overflowed. The position of the pipe is located higher on the tank so that no sludge is able to flow into the clarifier tank. The valve of the pipe should be filled open because if the valve is malfunctioned, the treated water will still be able to flow into the clarifier tank without causing the aeration tank to overflow.
Let me continue with the proposed control for sludge storage tank. Sludge is a byproduct from the treatment. The tank is not only acting as a storage for the sludge solution, it also blends to thicken the waste-activated sludge, primary sludge, imported sludge, and scums before further processing. The final disposal of the sludge is used as fertilizer, deposition at waste disposal sites, incineration on site, and part of the energy generation. Cascade control is being introduced for the new process control in a sludge holding tank. There are two controllers and two measured variable sensors. The level control is the primary control, while the flow control is the secondary control. The primary controller is the one that is driving the set point, and the secondary control is the controller that is receiving the signal from the set point. The final control element is the valve for the sludge disposal outlet. This process is to control the level of the sludge solution in the tank. By doing this, it can prevent the overflow of unwanted product to the other areas. The valve using in this process control is a fail open valve. It is used to prevent the accumulation of unwanted solution in the tank when anything goes wrong. Level control is being introduced in the cascade control. It is the primary control where it detects the current solution level in the tank and sends the signal through a transmitter to compare with the desired set point. After comparing, the signal will be sent to the flow controller. Next, the flow controller is the second controller in the cascade control. First, it detects the outlet flow rate from the tank and the signal is being sent to the flow controller. The flow controller will match the flow rate with the set point from the level controller. The flow controller will decide whether the valve should be opened or closed more. The advantages for this process control. By using cascade control, it will respond faster and more effectively to the disturbance. It is because the inner loop is both closer to the source of the disturbance and faster than the outer loop. This combination allows the process to upset more quickly. Besides that, the reason why the outlet of the sludge to disposal is at the bottom of the tank is to prevent the settlement of solids in the tank.
Clarifier tank is one of the major equipment in a wastewater treatment facility. Here we are going to talk about the process control within the clarifier tank. Firstly, there are two types of controller and transmitter here. The level transmitter and controller and the sludge level transmitter and controller. There are feedback controller. For example, the sludge level transmitter will detect the level of the sludge at the bottom of the tank and take corrective actions by calculating the output and transmit it to the control valve at the sludge output of the stream. However, for the level transmitter and controller, it will measure the level of the tank, and if it is approaching full capacity, the transmitter will send an electric signal to the level controller at the control valve located at the output effluent stream to increase the output. This is to ensure that the treated water does not overflow from the tank. Hence, when the level of the tank is at low capacity, the transmitter will lower the output of the effluent stream. The advantages of feedback control firstly is that it can reduce the system sensitivity of external substances. And next, a change in the performance of the system that is caused by parameter variations can be greatly reduced. Furthermore, another advantage of a feedback control is that the steady-state error in the system will be relatively small. The transient behavior of the process can also be easily manipulated in a feedback control system. Lastly, the feedback is compared with the desired state so that it can take corrective measure as well.